Hi guys, I'm gonna try to explain the serine proteases a little bit. So I guess first off, I had this from the Thursday slides. So if you see right here, the serine proteases, my picture for that, the acylation step and the deacylation step, and it's just a preview to BCHM462's like very long mechanisms and pathways. So this one's not that tricky, honestly. I'm going to try to let's see. I'll try to explain this using a whiteboard because I know. Whoops, wrong thing. Sorry. Let's share this whiteboard and explain this a little bit because my handwriting might have been hard to read. Yeah, I'm a little bit rusty, but one, you just have an acylation step. So you can split this into two main components. You have an acylation and a deacylation step. I would just recommend, so you form ester linkages, and then deacylation, you break the ester linkages. And what they mean by ester is like a tetrahedral intermediate you form. Sort of. So you have these two components, I guess. Yeah, I would just recommend annotating things through yourself because that really helped me explain this on the exam question. Let's see, 3N. So this is amino acid. So this is aspartate, 102. I don't think you need to know the residues too much in detail. So carboxy group and terminus. And there's a hydrogen sticking off of that. Lone pair here. Because histidine usually functions as a base or acid, general base or acid. This is histidine 57, and you can see here because of the lone pair, it is functioning as a general base. And then the last residue for the catalytic triad. I take things more of an orgo approach, so I don't know if you'll find this helpful. And this is serine. There's one up here. So this is serine 195. And these three make up the catalytic triad. And I don't know if this is too bolded. Okay, so I'm just going to go through this quickly based off my drawing to how I understood it. So you have an amino acid sequence. I'm going to abbreviate it. So you have a CN, you have NCC. That's the directionality of a peptide, as you might recall. So there's a amide right here. You see that amide bond, peptide bond, partial double bond character, amide. So that goes from way long ago. Kind of reviews stuff from long ago, which is why I kind of like this. So you have an NCC direction. So we have a polypeptide, and this is just a part of it. Okay, so then once we have this, I guess the first thing we want to do, I would try to keep this video short, but you can put it on 2x speed. I kind of miss making videos. I did a few last semester. This is not a GSS requirement, but I just feel like doing it, so you guys can review later. So you first form a tetrahedral intermediate. So you're going to attack this electrophilic center, partial positive, and this is a negative, so it's a nucleophile. This reminds me of Orgo too, and I'm paying for that lab right now. So what you want to do is use the serine. So this is the serine, and the serine 195 acts like the nucleophile. I would really highly recommend try to do this on a whiteboard and explain it to yourself a few times, and then you'll be able to explain it reasonably quickly on the exam in words. And then once you do that, so I would annotate this. So one, what you are doing is you're going to form tetrahedral intermediate. And the serine becomes attached. Also, just for your reference, I'm basing this off of my own drawings, which are in the slide, but adding a little more explanation, verbal explanation to it. Okay, so you have this R group here. Oh, also R group is just a side chain, so this is any amino acid in a polypeptide. And now you have oxygen attached, and then this is attached to here. So I count 1, 2, so tip, and this center, 1, 2. So this is a center which is attached to the carboxy and the N-terminus. And then you can see the serine is attached right here. So this is serine 195. Now it's attached to the amide carbonyl carbon. Okay, so that's the first thing you do. And then once this is an intermediate I just called it I on my diagram. And then what you now have to do is you have histidine. Okay, so what we want to do now is we want to create a good leaving group because this is a tetrahedral intermediate, and you have that oxyanion O minus, and then you can reform a carbonyl, and we want to kick off a good leaving group, but NH is not a good leaving group. So what we want to do next is we'll take, I'm going to actually use green because that's what I use on my drawing to help you easily follow. We're going to take the histidine as a general acid. Also, I use bond line structure because I'm just used to this. I know Dr. Puxdellus likes using the atoms, so it draws out the C's and H's. So you should be familiar with both. So what happens is histidine protonates amide N group to make a good leaving group. Functions as general acid. Oh, also, I just realized I skipped a step. So what you need to do, so serine isn't just deprotonated like a nucleophile. So the original step you need to do here, oops. So I guess this should have been step like 0, like a preparatory. So I'll just add, oops. So 0, step 0. So what you want to do is you take the general base and you protonate it using the serine. Protonate histidine 57 to make it a general acid and form serine 195 nucleophile. So that's step 0, I guess, to prepare, and then you do step 1, intermediate, then 2. And then what you simply need to do is just kick off the leaving group. So this is step 3. Whoops, I'm gonna draw the intermediate. So okay, so then next you have this C and H2 plus, so it's now a good leaving group, BHC double bond O, or it's still attached to serine. Okay, so what we want to do is now reform this. Oops. So we're going to reform, kick off the leaving group. Reform. It should not say reform tetrahedral intermediate, that's a mistake. Reform carbonyl. Oops. Guess I had a mistake last year. Oh, okay, and then the next step, after you do that, now you get double bond C, 3 plus. I flipped the molecule, by the way. Flipped it. I just flipped it. As you can see, the R group is down here. I just flipped it like 360. Flipped it like that. It doesn't matter. And then what we now, so now what we have is we have this plus you have this H2 and C, C, R, H, H. So what you did here is you cleaved the amide bond right here. And you have this residue has the H2N. So now you have this good leaving group became a amino terminus. And right here where you reform the carbonyl, you have this O still attached here, but this will become, I guess right here, this will become your C terminus, carboxy terminus. Well, hopefully that was helpful. And oh, I forgot one last thing. So your aspartate, so what does aspartate 102 do? So now you have a positive charge on the histidine right here when you form a general acid. So you formed, oops. So right here you formed it always takes a long time to draw histidine. So it's positive charge here. So this is a positive charge, and so the aspartate, this is the general base from step 0. So what your aspartate does is you have this O minus carbonyl so this will cause some stabilization. So aspartate 102 stabilizes the newly formed positive charge on histidine. Because remember, histidine existed in this original as just the general base, so it's not usually stable, it's just acid. So then aspartate 102 does that. So this is important because you want to know the function of aspartate as a stabilization. Serine is your nucleophile, and histidine functions as your general base and acid. So those are the 3 functions that you should mention in any explanation. So I guess this is part A is done. So you have cleavage. Ooh, whoops. So you have a cleavage after the acylation step, and you form the ester linkage. So then now we want to go to deacylation. So there are 2 functions here. Form ester linkage. As you can see on the left, this is the ester where I circle carboxy, and you have cleavage. So this is step 1. Step 1 is complete. Whoops. Okay, so hopefully that helps. Okay, and then after you have these 2 formations, what you want to do is deacylation. So what you need to do now is you have this weird thing formed here. Don't know. I'm gonna try to. Okay, so I just copied and pasted that here. And then now all we need to do so you have a serine. This originally originated from serine, and it's attached to the polypeptide. Serine attached. And then once you have this, all you need to do is now you want to reform another tetrahedral intermediate. So I'm sorry, not tetrahedral intermediate. I do not know why. Or actually, yes, you form a tetrahedral intermediate, but this time your nucleophile, second time, your nucleophile is actually water rather than, because it's a carboxy, so you just want water instead of the serine. So the second time around, now it is water. So this will be step, I guess, that was step 3. So I'm going to say step 4. Use water as nucleophile to attack carbonyl, I guess the ester, and form tetrahedral intermediate. So what you're going to do is use water as a nucleophile. I'm just going to draw all the bonds right here. So water is going to come in here, going to kick here up, and it's just like an orgo 2 mechanism. This is going to be like the nucleophile. I'm going to erase this a little just to not get confused. Okay, and then once you have that, my mistake. So basically, water isn't a good nucleophile, so you need to depronate it first. So what you will have, I guess you can just simplify this. You have, remember that now your histidine 57 is a general base because it was deprotonated. It functioned as an acid earlier, and now it's now a general base. So it will go acid, base, and it will rotate. So you have a carboxy group here, you have the NH3 amino acid group, and then what you should have these structures memorized. And what you have here is, I guess, I'll just show this extra step, even though it doesn't really matter. So you form an OH minus hydroxide, and hydroxide will attach that as a good leaving group. So I guess so that part A would be create good nucleophile from water, and then the part B is like use OH nucleophile. Okay, and then once you do that, remember there's an acid-base reaction going on here too. So once you do this, you protonated the histidine 57, and what you're having here is histidine 57 is now a acid. Sorry, I have two H's bonded there on the picture from when I drew it on the board, and that's wrong. I guess just found another mistake right now. Oh well. I was rushing then and I was concussed, or I recovered from a concussion, so I guess I had some errors. So now histidine 57 acts as general acid and protonates serine leaving group. So now instead of the water, I guess the proton transferred from the water to the histidine 57, and histidine is acting as the general acid. You're not using water directly as the acid. I guess it's a facilitator. And then what you have here is NC O minus, so you form the tetrahedral intermediate. Oh, I'm missing a charge there in my drawing too. Oops. Yeah, so now you have OH attached right here, and then all we want to do, so we have an oxyanion hole. That's another thing to mention in your mechanism. So this is oxyanion hole. So glycine and serine. Don't know where the glycine is coming from, but serine, the serine helps stabilize. So the amino groups, like the NH3 plus groups, help the positive charge because it's negative here. It helps stabilize the oxyanion hole. So this is kind of going on simultaneously with this. Okay, so what we now do, so I guess this is step 5, histidine acts as a general acid and protonates serine leaving group. Okay, so basically what we're having here is this H, and we want this to be the leaving group now, because this is the serine part, and we want to restore serine because serine is catalyst. So catalysts always have to be restored. So that's a good way to double check you did things right. So basically you reform your I kind of skip steps. You can do it separate or mesh it together. That's what kind of biochem does. But I'll just show the leaving group forming because I like it methodological and just not skipping steps. Even though it is a lot, and you probably remember this from Orgo. So instead of this being the leaving group, because this was what was attached, we're just switching it so we can reform a carboxy group, not make this the leaving group, because then you're going backwards. It's just from Orgo. Kind of miss Orgo. Okay, so this is an intermediate. And then once you have that, also remember you still have your oxyanion hole here. It's still being stabilized by serine NH3. So I guess the NH3 plus from serine. So this is serine. It's like stabilizing that. Another serine or glycine, and there's another glycine here somewhere. Just remember these are just found in the molecule. So remember proteins are big, so there are things that are close to it, residues close to it. So glycine looks like this. Yeah, it just has 2 H's because it's not chiral. So that's stabilizing that charge right there, the oxyanion hole. And then once you do that, all you need to do, it's pretty simple. Okay, so now we're going to kick off the leaving group. And then now you have, it's not cleavage exactly, because all you did now is now you have an OH, so you have a carboxy group. And you might wonder why it's protonated. Well, you can deprotonate that. And you have an OH here. O minus. Okay, so then now you have this plus this. And you reformed the serine. So here's serine. This is serine 195 reformed to reform serine 195 catalyst. Members catalyst. So you have it restored right here. And then now you have your member proteases cleave things. So this is protease cleaved the amino acid residue, similar to endopeptidases. So it cleaved it at amide peptide bond, basically. So now your polypeptide is shorter. Okay, so I just wanted to highlight the serine 195 is reformed from right here. So that was serine 195 and it got restored. But what about the other catalysts? So your histidine 57, which is right there. So it acted like a general acid here. So now we just need to show that it reformed the original state, which was a general base. And I forgot to show that here. But basically, let's use a different color. The histidine. Sorry for messy handwriting. His 57 restored. So it's now a general base and it's restored, so we check that. Okay, so we have serine and histidine, but what about the, sorry, it's in yellow here. What about aspartate? So aspartate is a weird one because all we did, oh, I'm not going to use yellow. I'll use pink. Okay, so aspartate 102 is kind of weird because all it did throughout is it stabilizes the positive charge of histidine. So I guess right here, when you have this positive charge, aspartate is also here. Oops. It's one down, that's how I remember it. There's a carbon in the middle. And then there's a carboxy group of this. So remember that this was stabilizing. Yeah, so remember this aspartate stabilizes. Let me just quickly write that. Aspartate 102 stabilizes his 57. It is general acid because it has a negative charge. Remember, aspartate 102 is negative charge. So it stabilizes positive charge when histidine is positively charged. So here's the aspartate 102. It was never really consumed because it was used for stabilization. Also remember, the aspartate also stabilized, I forgot one last thing. Okay, so the aspartate also stabilizes this positive charge right here. So this positive charge on the serine leaving group stabilized also by aspartate 102. Yeah, so pretty much aspartate just stabilizes everything. Okay, so I don't want to make this too long because I think that was already like an hour. So here's what I'll do. I'll just circle this deacylation step. So this is like part 2. And then I hope that helped. I end up writing bigger all the time. And then I think you can notice that the catalytic triad always remains there. And it's not consumed because it's a catalyst. So I guess main takeaways. You need to know the function of catalytic triad. I'll zoom in. Okay. So what that means is aspartate 102 doesn't really get changed at all. It stabilizes. So the carboxy group, the side group, like the R, basically side chain. Stabilizes any positive charges. Whereas the Serine 195 was the first time. And the acylation, and then for the deacylation. Because in order to deacylate, you need to replace it with another group. And then remember that the cleavage with protease occurs at the amide bond CN. So which chain to which N? So N is bonded to that carbonyl and is bonded to an alpha carbon. So the one that you actually depronate, you cleave, is not between the alpha carbon and, but the one that's between, right here, the amide bond. So between carbonyl. And this happens after part 1, not part 2. Part 2 is just restoring autocatalysts. Part 1, which is and the deacylation. Restore it, yeah. So I think maybe this helps. I might bring back some orgo memories. So I hope that helps, and I would just stay on right here for a little bit so you can pause the video. Okay. Or screenshot that. I'm going to zoom out here, so you're welcome to screenshot this. This is the acylation. You can feel free to screenshot or pause the video. And then here is acylation stuff. Yeah, hopefully that was helpful, and that's it. Hope to see you at GSS next week for the last one. And hopefully this clarified any confusions in my handwriting. I'm gonna go back to Google slide. Any confusions in my handwriting in this slides, and like the mistakes I had. For instance, right here it shouldn't be NH2, it should just be NH+. And I think I found, I said you form alkoxide is just the O-, by the way. And I think I said reform tetrahedral intermediate, but that should be carbonyl. I think there was something else maybe, but I don't remember. Can I go backwards? That was the funny story. Okay, so just, this is important. You don't have to draw out the entire mechanism, just know how it works, be able to explain it, draw out the entire mechanism for practice. It's not that bad. I was able to do it within an hour. Like, I think it took like 15 minutes or so. So I would just recommend doing that. Spend 15 or 20 minutes doing it, draw it out, use colors, annotate the steps. Hopefully my video makes it helpful in the screenshots here. And I would just repeat this with the RNA hydrolysis, RNA mechanism, and DNA replication for yourself, and that will really like help you. I can't. That was like an example. Yeah. Yeah. And then thanks for a wonderful semester, and if you can fill out the form on feedback for your last GSS, that would be great. That's it.